Anything that you want me to talk about again? The entire class was implicit function. That entire class was differentiation of implicit function. Were you there in the class? So, but all along, every 3 minutes I kept prompting, did you understand? Did you understand? So you'll have to be very specific about what you did not understand. You know, I'm willing to explain anything, but you'll have to tell me what you did not. What an implicit function is?
Differentiating cos y with respect to e to the power x.
Cos y with respect to e power x. I never differentiated cos y with respect to e power x. Sorry?
Cos y equals to ln x squared plus x.
If I want to find dy dx here, right? So sit down. ddx of cos y is ddx of ln x square plus x, right? But what's ddx of cos y? It's not minus sin y. एक minute. It's minus sin y dy dx. You didn't understand this?
That was only the problem which I was having.
Okay, so then that will be the problem that I will address. Alright. So then, if I propose ddx of cos y, then what I do is, I differentiate cos y with respect to y and then y with respect to x. That was courtesy chain rule. Right? But what is derivative of cos of Ahmedabad with respect to Ahmedabad? Minus sine of Ahmedabad. Right? So cos of Ahmedabad with respect to Ahmedabad would be minus sine of Ahmedabad. Sine by. And dy dx would be dy dx. Absolutely. What else? Okay. So then I write cos y as minus sine y dy dx. That's the left hand side. Right? Now the right hand side is perfectly applicable, perfectly eligible for chain rule application. So I go from outside to inside. The outermost is a log, so it will be 1 by whatever is inside, 1 by x squared plus x, and then x squared plus x with respect to x is going to be, so that's dy dx equal to minus 1 by sine y x squared plus x into 2x plus 1. Did you understand the rest of it? Sure? Huh? Anything else?
So integration is new formula, integral of 1 by x into root of 1 over x square minus 1 is dx equal to sine inverse of x plus c.
Second inverse. 1 by x root x square minus 1 is second inverse x. Sumit, duster. See, in differentiation, I established that ddx of sec inverse x is 1 by x root x squared minus 1. This was a result that I gave in my class on derivatives. Did you understand this? No. This is what you did not understand, right? So, well, y is sec inverse x and I propose to find dy dx, right? Now, this would lead to sec y equal to x, right? Y equal to sec inverse x means sec of y must be equal to x, and then let me differentiate both sides with respect to x, so I get, or rather you might want to differentiate with respect to y also, right? So you have like a dx dy that is differentiating sec y with respect to y, that will give you like a sec y tan y, right? This is like sec y, tan y is root sec squared y minus 1, that's tan y. But sec y is x, and sec squared y minus 1 then is like a root x squared minus 1. So that's dx dy. Therefore, dy dx is going to be the reciprocal of dx dy, which then would be like a 1 by x root x squared minus 1. Dy dx means ddx of sec inverse x. ddx of sec inverse x is this. And therefore, I could also have said ddx of sec inverse x plus c is that, right? And therefore, when I write integral 1 by x root x squared minus 1, then I'm seeking the I told you the concept of primitive and derivative, right? Did that? So I'm seeking the primitive of this. I'm seeking the function which upon differentiation gives me this function. That's evidently this function. That's going to be then sec inverse x plus c. Right? Yeah. ddx of log x is 1 by x, or ddx of log x plus c is also 1 by x. So when I say integral 1 by x dx, what's the question that I am inquiring? Find a function which upon differentiation with respect to x gives me 1 by x. What's that function? Log x plus c. Now that's another issue. I just refined that further so that it falls within the domain of definition always. Reason I put this modulus is in the event x is negative, that negative is eaten away by the modulus sign, leading to logarithm of that number being well defined.
So will this formula work even if x is negative?
Yes, it will work even when x is negative. It does not matter because the modulus will take care of that. Even when x is negative, modulus of x will still be positive. You've seen that class on modulus? So modulus, the output of a modulus operation will always be positive or non-negative in fact. Right? Now, ddx of e power mx by m plus c. When I differentiate this, this is going to be ddx of 1 by m e power mx plus ddx of c. C is a constant, goes into oblivion, 0. This is like the 1 by m scoops out, so 1 by m ddx of e power mx plus 0. This is 1 by m. Now go from outside to inside. Outermost e power will give me e power, and then mx with respect to x will give me m. Right? So do you realize that when I differentiate e power mx by m plus c, I get a e power mx. Means integral e power mx is find a function which upon differentiation gives me e power mx. What's that function supposed to be? E power mx by m plus c. Anything else? No? So, shall we proceed? Now, what I'm going to introduce to you is the algebra of differentials. The algebra of differentials. First of all, let me tell you, delta of something, like I've been saying all the time, is change in something. Well, when I say something means the same thing as this thing, right? And it's a finite change. It's a finite change. When I say d of something, d of something, that's also a change. That's also a change. But this change is very, 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 very small, as small as you can imagine. When I say d of something, it's an extremely small change, as small as you could imagine. This change comes closer and closer and closer and closer to zero. It's a very, 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 very small change. D means not a finite change, but a very, very small change. And as small as you can imagine, as small as you can conceive. That's d of something. As close to zero as possible. As close to zero as possible. That's what physically d of something means. And so this is also a change, but this is a finite change. A finite change, right? It could be big, small, whatever. But d of something means an extremely small change, as small as one could imagine. And this d of something is referred to as an infinitesimally small change. An infinitesimal change is referred to as an infinitesimal change. Infinitesimally small change. It's an infinitesimally small change. That's d. In contrast to delta, this is delta, which is a finite change. D of something is a very, very small change, as small as one can imagine. That's d of something. Now, to give you a feel for this, let me first give you a feel for this. Can I wipe this off? Say, for example, take y equal to fx, which is sin x, alright. Now, what we did was, we allowed x to grow from x to x plus delta x. We allowed x to grow from x to x plus delta x. Then, the change in x was this. This is change in x. However, this was a finite change in x. This was a finite change in x. Now, sin x, which is y, went from sin x to sin x plus delta x. Right? The change in y was final value of sin x minus initial value of sin x. Final value of sin x is at x equal to x plus delta x. Initial value of sin x is at x. So change in y is like a sin x plus delta x minus sin x. That's a change in y when the change in x is delta x, right? And then we did the following. We said delta y by delta x. Change in y divided by change in x. That was like this divided by delta x and so on and so forth. And then we caused. And this, like I said, was representing the average rate of change of y with respect to x across an interval x to x plus delta x. And then we did the following. We started to shrink delta x. We made delta x smaller and smaller and smaller. As we made delta x smaller and smaller and smaller, we represented it mathematically as delta x tends to 0, right? We started from, let's say, a value of delta x equal to 0.01. We moved on to 0.001 and then 0.0001 and then 0.00001, then 0.001 million zeros, and then 1, and then 5 zillion zeros, and then 1, and so on and so forth. We came closer and closer and closer and closer to 0. And then in the process, delta y also came closer and closer and closer to 0. When delta x shrunk, delta y, change in y also shrunk. Now, although this is a property of a function. This may not always happen, but then for the functions that we would be dealing with, as change in x becomes smaller and smaller, change in y will also become smaller and smaller. And such functions are called continuous functions. When change in x becomes smaller and smaller, we find that change in y also becomes smaller and smaller. Then that category of functions are called continuous functions. Continuous functions. They are continuous functions in which this property is respected. Continuous functions. But don't bother too much about continuous functions and so on and so forth, because then we would be getting into a little more rigorous understanding. I want to skim away from it for the time being. So in any case, for the functions that we would be dealing with, as delta x becomes smaller and smaller, the change in y also becomes smaller and smaller and smaller. And then change in y by change in x, however, comes closer and closer and closer to a finite value, comes closer and closer to a finite value, L. As delta x becomes smaller and smaller and smaller, and therefore also delta y becomes smaller and smaller, delta y by delta x, however, comes closer and closer and closer to a certain number, L. And this L was referred to as an instantaneous rate of change of y with respect to x at x, right? And we wrote that statement as limit of delta y by delta x as delta x becomes smaller and smaller and smaller. And this was represented as ddx of y. This statement was written as ddx of y, an instantaneous rate of change of y with respect to x at x, right? Now, so far, all along I have been telling you, ddx is an operator. It's capable of acting on functions. It's capable of acting on functions to produce a certain output. For example, when it acts on sin x, it produces a cos x. When it acts on cos x, it produces a minus sin x. When it acts on tan x, it produces a sec squared x. So then, I have kind of inadvertently forced you to believe that ddx is one entity and sin x is the other entity. That's ddx of sin x, right? So ddx I have looked upon as one thing which is acting on another thing. What thing? Sin x, to produce an output called cos x, right? But now I would allow your minds to wander a little bit and not get confined to this understanding, just this. In this description, delta y comes closer and closer to 0. So when delta y comes closer and closer to 0, that's the change in y becomes smaller and smaller and smaller. We can look upon delta y as dy, an infinitesimally small change in y. I can look upon this as gy, an infinitesimally small change in y. And delta x also begins to shrink, comes closer and closer to 0. And I can look upon delta x as delta x comes closer and closer to 0 as gx. So now, what I propose is, instead of calling it ddx of y, I would now want you to think afresh and look upon this as dy by dx, an infinitesimally small change in y divided by an infinitesimally small change in x. An infinitesimally small change in y divided by an infinitesimally small change in x, which in turn also turns out to be an instantaneous rate of change of y with respect to x at x, right? Now, you have your calculators with you, right? You have your calculators with you. Take out your calculators, put it in the radians mode, and let's get ready for some action. And the fact that ddx of y is now being treated as a ratio dy by dx makes it eligible for chain rule. Now you would realize that chain rule seems within comprehensible limits, because now if I say like dy dx equal to dy dt into dt dx, then if looked upon as a ratio, this seems good. This seems good, because then you can cancel a dt dt and it will be like dy by dx, right? The chain rule, in fact, is a baby of this understanding of differentiation, right? Ratio of two infinitesimal changes is like the derivative, is like ddx of y, right? So the chain rule really emerges out of this comprehension and this notion of differentiation, ratio of two infinitesimally small changes. All right. Now, so anyone who's fast with the calculator would have to just tell me some numbers, which I would map on the board for the rest, right? So who's very good at using the keys on the calculator? Okay, you're very good. All right, so you are the class rep for this. Now, ddx of sine x is cos x. All right, ddx of sine x is cos x. I want to look upon this as t of sine x, an infinitesimally small change in sine x caused by a change in x, which is dx. When x changes by a very, very small amount dx, sine x, ratio of change in sine x by change in x is cos x, right? Say x is pi by 3. Say x is pi by 3. Okay. Then the initial value of sine x is sine x is sine pi by 3. Let me call it pi by 6 so that it's easier to compute, right? 30 degrees, which is half. Now, I change x by a small amount. I change x by a small amount. Change x by an amount, pi by 50. Change x by an amount, pi is 3.14 approximately. So, change in x is pi by 50. What is the new value of x? The new value of x is pi by 6 plus pi by 50. Pi by 6 plus pi by 50, which is like 56 pi by 300. That's a new value of x. 56 pi by 300. Now, what's the new value of sine x? What's the new value of sine x? Sine 56 pi by 300. That's a new value of sine x, right? What is it approximately? 0.553. Okay. Now, what is change in sine x? Change in sine x. Final value of sine x minus initial value of sine x. So 0.053. The initial value of sine x was 0.5. The final value of sine x was 0.553. So 0.053. 0.053 is the change in sine x. Yes or no? Right? So change in sine x is 0.053. Right? Yes or no? Change in x is pi by 50. Pi by 50. which is like 0.314 divided by 5, which is 0.0628. 0.0628, that's a change in x, right? Now, change in sin x divided by change in x. Can you just calculate this? 0.053 divided by 0.0628. Can you just calculate this and tell me? 0.8439, right? Change in sin x by change in x, right? Change in sin x by change in x. This is change in sin x by change in x. That should be cos of x. Now, cos of 30 degrees. Cos of x. Here is cos of 30 degrees. That is root 3 by 2, 0.866. This is 0.8439. This is 0.866. Do you realize? Right now, change in sin x by change in x is 0.8439, and that is cos of x, which is 0.866. They are close to each other, but they are still not equal to each other. Now, the next operation that you perform is, so there is still some difference, but it's close, 0.8439 and 0.866, right? Change in sin x by change in x is approximately cos of x, already, right? But there still is some gap between this ratio and cos of x. See, we expect this change in sin x by change in x to be cos x. But what does this statement say? It says that change in x should be very small. Find the corresponding change in sin x, and that ratio should be exactly equal to cos x, right? Now, what I do is, I change these numbers. Okay. Pi by 500. Alright. X is pi by 500. Then, the new value of x becomes 506 pi by 3000. That's a new value of x. 506 pi by 3000. That's a new value of x, right? Can you just tell me the value of sin x for this value of x? Can you tell me the value of sin x for this value of x? Can you? Sine of 506 pi by 3000. Point 54. Okay. Now, what's the change in sin x? What's the change in sin x? 0.054. 0.054. What's the change in x? Pi by 500. Right? Compute this ratio. Now compute this ratio. Change in sin x divided by change in x. Can you just tell me what this number is? Point 0054. Yeah. 0.0054. Right.
0.8592. 0.8592.
Hey, do you realize it's now come closer to 0.866? Now it's come closer to 0.866. Do you realize this? Huh? Now, my contention is, if you decrease delta x further, now let's say if you make it pi by 5000, right? And again compute new sin x, old sin x, change in sin x by sin x, it'll close in. It'll come even closer to 0.866. You make it pi by 500,000. This ratio would again become higher, and it will come closer and closer to 0.866. That means when delta x is made smaller and smaller and smaller, the change in sin x by change in x will come closer and closer to cos x. Just this. And eventually when delta x is made as small as you can imagine, then that delta x is written as dx. And then the change in sin x is not written as delta sin x, is written as d of sin x, is written as d of sin x. That means when the change in x is like really small, call it dx. When the change in x is really small, infinitesimally small, call it dx. Then the change in sin x, which is also really small, is d of sin x. The change in sin x is cos of the original value of x into change in x. This expression would be more and more accurate as the change in x is becoming smaller and smaller and smaller. The change in x becomes smaller and smaller and smaller. The validity of this expression becomes more and more superior, right? Do you understand this? So change in sin x is cos x into dx. So this d is actually an infinitesimally small change. This change in sin x, infinitesimally small change in sin x, is caused by an infinitesimally small change in x dx and is equal to cos x into dx. So now we can look upon that dy dx as actually ddx of y is actually dy by dx. It makes sense to look upon the derivative also as a ratio of dy by dx, an infinitesimally small change in y divided by an infinitesimally small change in x, right? Now, all of you are fine with this, right, so far? Let's say I write, first of all, let me tell you that ddx of some function fx, rate of change of fx with respect to x, will henceforth would be written as f dash x. F dash x would mean rate of change of fx with respect to x. This is the notation followed. This is just a notation. Instantaneous rate of change of fx with respect to x is referred to as f dash x. Alright. Where fx is the primitive and f dash x is the derivative. Fx is the primitive and f dash x is the derivative. So then g of fx, so this could be looked upon as g of fx divided by g of x. G of fx is like f dash x into dx. F dash x into so whenever you have to say d of something, that's going to be derivative of that thing into dx. If I say d of fx, it's going to be derivative of that thing into dx. For example, then if I have to say d of sin x, then what I would do is derivative of sin x with respect to x is cos x. So I can say that that's equal to cos x into dx. D of e power x is going to be derivative of e power x, which is e power x into dx. D of tan x dx. D cot x dx. D of c, where c is a constant. 0, because there is never a change in a constant, right? So d of c is 0, where c is a constant. D of ln x 1 by x dx, and so on and so forth. So each time you have to say d of something, that change in something, an infinitesimally small change in that thing, and that's going to be the derivative of that thing into dx. Derivative of that thing into dx. Change in this thing occurred. Why? Because there was a change in x. A change in x, which is dx, was responsible for a change in fx. And the relationship that we arrived at is, when the change in x is really small, call it dx. Then the change in fx, which is also really small, is like f dash x into dx. That's what this implies, right? And the inverse of this operation, is, if I had like a cos x dx, and I want to write this as d of something, then I'm going to look upon this as the integral of cos x with respect to x. I'm going to look upon this as the integral of cos x with respect to x. What am I going to fill up here? I'm going to fill up the integral of cos x with respect to x, which is sin x plus c in general. Sin x plus c in general, right? Because d of sin x plus c, d dx of sin x plus c is cos x. So d of sin x plus c is cos x dx. If I had like sec squared x dx, that is d of tan x plus c. Now it's my prerogative. In these cases, I can choose c very liberally. It's my choice. Sometimes I can choose c to be 0. Depending on the situation, I can get a little flexible about my choice of, right? C could be 0 on certain occasions, or c could be some other value depending on what we are dealing with, right? But in general, this, right? If I said sin x dx, that's going to be d of. If I said e power mx dx, that's going to be d of plus c, and so on and so forth. So if you're going from like a cos x dx to d of something, then this something is going to be the integral of this thing with respect to x. This is the integral of this thing with respect to x. This is the integral of this with respect to x. This is the integral of this with respect to x, and so on and so forth. Right? Now, there are some regulations related to this operator d. D, like I said, is an infinitesimally small change and is called the differential operator. This is called the differential operator. D of something means an extremely small change in that thing, right? Now, some algebra related to differentials. Suppose there are two functions, u1 and u2, two functions of x, u1 and u2, ddx of u1 plus u2, where u1 is a function of x and u2 also is a function of x. Then what we learned in differentiation is that this is going to be du1 dx plus du2 dx. Right? Now that I'm looking upon this as a ratio, p of this, small change in this divided by a small change in x, right? Infinitesimally small change in x. I can multiply throughout by dx. Dx comes closer and closer and closer to 0, but is not 0. And that's the reason I can multiply or divide by dx as I want, right? Because it's not 0. So let me multiply throughout by dx in any case. So d of u1 plus u2 is d of u1 plus d of u2, which means in verbose you might want to spell it out as differential of a sum would be sum of the differential. See, this is differential of a sum of two functions. This is differential of a sum of two functions. That would be sum of the differentials. That would be sum of the differentials of the two functions. Clear? Right? So now, if I had like a d of sin x plus log x, d of sin x plus log x, that's going to be d of sin x plus d of log x. How about this? D of sin x plus d of log x. Hey, but d of sin x is something into dx. What thing? Cos x into dx. D of sin x is going to be cos x into dx. d of log x is going to be 1 by x into dx, etc. Right? So that's rule number 1. Differential of the sum would be sum of the differentials, Clear? Can I wrap this off? Similarly, if you had a difference, very clearly, ddx of u1 minus u2 is ddx of u1 minus ddx of u2. Therefore, d of u1 minus u2 would be d of u1 minus d of u2. Differential of the difference would be difference of the differentials. This is differential of a difference of two functions. That's difference of two differentials. Difference of two differentials. That's rule number 2. Are you all okay with this? ddx of u1 u2, product of two functions, ddx of u1 u2, derivative of the product of two functions is first function into derivative of second function plus second function into derivative of first function, right? So it's like u2 into du1 dx plus u1 into du2 dx. That's the product rule of differentiation, right? Multiply throughout by dx. So then d of u1 u2 is u2 d of u1 plus u1 d of u2. Differential of the product of two functions. Differential of the product of two functions would be differential of first function into second function plus differential of the second function into first function. Right? That's the product rule of differentials. That's the product rule of differentials. Write this up. ddx of u1 by u2, quotient of two functions, derivative of the quotient of two functions, derivative of numerator into denominator minus derivative of denominator into numerator divided by denominator squared, right? Derivative of numerator into denominator minus derivative of denominator into numerator divided by denominator squared. Multiply throughout by dx. That means d of what? D of the quotient of two functions. Change in the quotient of two functions is going to be u2 du1 minus u1 du2 divided by u2 squared. That's the quotient rule of differentials. That's the quotient rule of differentials. Got me? Can I wrap this off? So differential of the quotient of two functions is differential of the numerator into denominator minus differential of the denominator into numerator divided by denominator squared, right? Now, evidently, if u is a function and c is a constant, if u is a function of x and c is a constant, then from the sum rule, it's going to be du plus dc, but dc is 0. So this is du. D of u plus a constant is d of u. D of u. Now, ddx of a times, a is a constant, let's say a is a constant, and u is a function of x, and u is a function of x. Then this a can come out of the derivative sign. So this would be a times ddx of u. A times ddx of u, which means d of au is a times d of u. So d times au is a times du, right? So that means this a can come out of the differential sign. This a can come out of the differential sign, which means if I had d of 3 sin x, then I can allow this 3 to trespass 3 times d of sin x, 3 times d of sin x. Got me? Now, once you understand these facts, then we are actually ready for a few more types of integrals. There would be a variety of integrals classified as follows. We have a function fx raised to a certain power m, where to begin with m not equal to -1. You'll realize why I stipulate this. A function raised to the power m where m not equal to -1 into f dash x dx, into f dash x dx. Now, f dash x dx is d of what? fx is d of fx, right? Isn't it? This is what I said to you right in the very beginning. Because ddx of fx is f dash x. ddx of fx is f dash x. So d of fx would be f dash x. So f dash x dx I can write as d of fx. D of fx. F dash x, this f dash x dx I could write as d of fx. Now tell me this, when m not equal to -1, what's t to power m dt? What's t to power m dt? T to power m plus 1 by m plus 1. Right? It's going to be t to power m plus 1 by m plus 1. Yes or no? This is going to be t to power m plus 1 by m plus 1 plus an arbitrary constant c, c. And that's the reason I said m not equal to -1, right? Hey, do you realize that now this falls within that classification? This is t to the power m dt, where t is fx. In this case, t is fx. So it's t to the power m dt, where t is fx, How about this, right? T to the power m dt, where t is fx. That's going to be t to power m plus 1 divided by m plus 1 plus c, where t is fx. So this is going to be fx to the power m plus 1 by m plus 1 plus, so integral fx to power m dfx is like t to power m dt, and that's like t to power m plus 1 by m plus 1 plus, right? And m not equal to -1, otherwise the operation would become illegal, right? So then the integrals that we are talking of belong to the kind where you have a function raised to a certain power not equal to minus 1, a function raised to a certain power which is not equal to minus 1 into the derivative of the function, Such integrals would be function to the power m plus 1 by m plus 1 plus c. Got me? For example, if I had like sin x to the power 3 by 5 into cos x dx. Do you realize that this is the same template, right? Function is sin x fx raised to the power m, which is 3 by 5 into derivative of sin x, which is cos x. So function raised to a certain power into the derivative of the function. It belongs to this category. So that's going to be function to power m plus 1 divided by m plus 1. Yes or no? Function raised to a certain power into the derivative of the function going to be function to power m plus 1 divided by m plus 1. So this is going to be like a sin x to power 3 by 5 plus 1. That makes it 8 by 5 divided by 8 by 5 plus Vedant, right? Vedant, fine with this? Function raised to a certain power into the derivative of the function. Function to power 3 by 5 plus 1 divided by 3 by 5 plus 1. That's the formula. Function raised to a certain power not equal to minus 1 into the derivative of the function. Function to power m plus 1 by m plus 1 plus c. Right? Now, so if I had like integral tan x to power 3 into sec squared x dx, what would this be? This is function raised to the a certain power, and what is this? This is the derivative of tan x, so it belongs to that template, and this is going to be tan x to power 4 by 4. Right, let's see. Right? What would this be? Integral sine 2x to power half. First of all, sin x cos x is what? Half sine 2x. 2 sin x cos x is sine 2x. So sin x cos x would be half sine 2x. Yes or no? Sin x cos x is going to be half sine 2x. Now, I'm so sorry. I just swallow something that I just said. Since I want to write it in that form, let's say I had just a cos 2x instead, because then it will not fall in the category that I am stating. Sorry about that. Take it as cos 2x. Now, what's the derivative of sine 2x? Huh? What is 2? 2 cos 2x. Go from outside to inside. Cos 2x into 2. 2 cos 2x is the derivative of sine 2x. The derivative of sine 2x is 2 cos 2x. Isn't it? Go from outside cos 2x into 2. Right? So then, but we just have cos 2x. But then it doesn't hurt bringing a 2 from nowhere, but then managing it out here. Right? You know why we did this? Because we wanted to make this the derivative of this. That's why we multiplied by 2. If I had not done this, What's the derivative of sine 2x? 2 cos 2x, but we just have a cos 2x. To reduce it to the known template, it becomes important for us to multiply by a 2 so that this becomes the derivative of sine 2x. But then this 2 has to be balanced by a 2 here because to maintain status of the expression, right? So now we have like a function raised to a certain power into the derivative of the function. This is a function raised to a certain power into the derivative of the function. So that's going to be function to the power half plus 1, that is 3 by 2 divided by 3 by 2 plus. So sometimes it may not, function raised to a certain power into the derivative may not be served to you on a platter. You might have to multiply and divide by things so that it falls within that classification. Got me? So in this case, we had to make an adjustment to the tune 2 so that we arrive at a form function raised to a certain power into the derivative of the function, and then we could readily write function to power n plus 1 divided by n plus 1 and so on and so forth. Are you all there with me on this? Alright, x square plus 2x to power 5 into x plus 1. What do I do to this? X square plus 2x to power 5 into x plus 1. Absolutely. The derivative of this is 2x plus 2. But we just have a x plus 1. So if I multiply it by 2, this would become a 2x plus 2. This is going to become a 2x plus 2 and would be rendered the derivative of this, right? So I multiply by 2, but then I need to balance it here because this was brought from nowhere, right? So I now have a function raised to the power 5 into the derivative of the function, right? So that's going to be power 6 by 6 plus, see? So sometimes in your attempt to reduce it to the known form, you might have to make adjustments of this kind by inspection, right? Okay, now tell me integral tan x minus x to power 1/3 into tan squared x. Tan x minus x to power 1/3 into tan squared x. Which is tan squared x, right? This actually is x squared x minus 1, right? So this really is the derivative of this because this is x squared x minus 1, right? So we really have it served on the platter right away. Function raised to a certain power into the derivative of the function. So that's going to be tan x minus x to power 1/3 plus 1, that is 4/3 divided by 4/3 plus see this tan squared x I propose writing as sec squared x minus 1. This tan squared x I write as sec squared x minus 1, right? What's the derivative of this? sec squared x minus 1, which is this. Right? So it's fx to the power m into f dash x. This is f dash x, the derivative of this. So function raised to a certain power into the derivative of the function is going to be function to the power plus 1 divided by power plus 1. Right? So that's going to be tan x minus x to power 4/3 divided by 4/3 plus c. Right? So we've explored cases where m is not equal to minus 1. How can we leave out the possibility of m being equal to minus 1? So let's try and design the case for m equal to minus 1. So when m is equal to minus 1, fx to power m would become 1 by fx. Fx to power m would become 1 by fx. That means the integral that we are talking of when m is equal to minus 1 is like f dash x by fx. F dash x by fx. That's a form of the integral that we want to deal with now. When m is equal to minus 1, that fx to power m would become 1 by fx. So what's the form of this integral? The numerator is the derivative of the denominator. The numerator is the derivative of the denominator, right? Now, like before, f dash x dx is d of what? Is d of x, right? F dash x dx is d of fx. So this f dash x dx I can write as d of right? Now tell me, what is this supposed to be? 1 by t dt. What is this supposed to be? Log mod t plus c is supposed to be log mod t plus, right? So is this not of the form dt by t, dt by t, dt by t, where t here is fx. This is the same as this. T is fx here, t is fx, right? So then this would be log mod fx. It's going to be log mod fx plus, see, log mod fx plus. Did you understand f dash x dx is d of fx? This is the result. 1 by t dt is log mod t plus c. Is this not of the same form? 1 by t dt, where t here is fx. This is the same as this. Instead of t, you have a fx here. So 1 by t dt, 1 by t dt, that's going to be log mod t. 1 by t dt is log mod t. 1 by t dt is log mod t plus c, right? T here is fx. So each time you encounter an integral in which the numerator is the derivative of the denominator, then close your eyes and write the integral as log mod denominator. Log mod denominator. Numerator, the derivative of the denominator, then the integral is going to be log mod denominator. Right? Clear? Now we're going to look at some standard integrals based on these facts. Integral tan x dx. See, this is not one that we've known so far. Integral tan x dx is something that I have not discussed yet, right? But now we are kind of eligible to deal with it. because this could be written as integral sin x by cos x dx. Right? Is the numerator the derivative of the denominator? Not yet. Not yet. But I can make it the derivative of the denominator. The derivative of cos x is in fact minus sin x. So why not push a minus here and make an adjustment there? So now, with this small little adjustment, we've caused the numerator to become the derivative of the denominator. And when the numerator is the derivative of the denominator, the integral becomes log mod denominator. So log mod cos x with a minus sticking out. Right? So this then is minus log mod cos x. Right? And then why not do the following? Log mod cos x. Allow this minus to occupy a place in the power here. That's property of logarithms. M log n is log n to the power m. Right? That's the property that we've deployed here. So this minus 1 goes there. Right? But cos x to the power minus 1 is 1 by cos x. That is sec x. That is sec x. Right? So this makes it like a log mod sec x plus c. Now this is a regulation integral and you got to remember this. Integral tan x dx is log mod sec x plus c. Integral tan x dx is log mod sec x plus. Got me? Can I wrap this off? Integral cot x dx cos x by sin x. This is ready for use because the numerator is the derivative of the denominator. So the integral is log mod denominator, right? The numerator is the derivative of the denominator. So it's going to be log mod denominator plus c. Right? So integral cot x dx is log mod sin x plus c. Integral cot x dx is log mod sin x plus. That's another standard integral that you want to remember. Okay? Can I wrap it up? Integral sec x dx. Integral sec x dx. This you may want to write as sec x into sec x plus tan x divided by sec x plus tan x. See what has transpired in the process. What's the derivative of sec x? Sec x tan x? Sec x tan x. What's the derivative of tan x? Sec squared x. Derivative of sec x is sec x tan x. Derivative of tan x is sec squared x. The numerator is therefore the derivative of the denominator and the integral would be log mod denominator. So this integral would be log mod denominator. Right? So integral sec x is log mod sec x plus tan x plus c. Another standard integral, you have to remember this. Evidently, we would now want to look into cosec x, right? Cosec x. Can I write this off? integral cosec x dx. Now check on this. What's the derivative of cosec x? Minus cosec x cot x. What's the derivative of cot x? Minus cosec squared with a minus here, plus cosec squared x. Plus cosec squared x. Do you realize then that the numerator is rendered the derivative of the denominator? The integral therefore would be log mod denominator. Log mod denominator. How about that? Right? Log mod cosec x minus cot x. Gain a result that you got to remember. Now, look at this. One integral that I have already told you is the following: 1 by 1 plus t squared dt. What is that supposed to be? Did I tell you this? Tan inverse t. Tan inverse t plus c, right? Have not discussed this? Plus c. Okay. Now, in contrast, we have a similar looking integral 1 by x square plus a squared dx. 1 by x squared plus a squared dx. What I do is, I write this dx. I take a square common from the denominator. I take a square common from the denominator. And then I end up getting 1 plus x by a whole square in the denominator. 1 plus x by a whole square is what I arrive at in the denominator, right? Now, for the numerator, d of x could be written as a into x by a. How about this? This x could be written as a into x by a, right? And then this a, by virtue of properties of differentials, this a can scoop out of the differential sign, right? This a can come out of the differential sign, is it not? So when this a comes out of the differential sign, it's sitting right here. And then this a with this a squared would cause it to become 1 by a, would cause it to become 1 by a. Now the form is dt by 1 plus t squared. Is it not of the form? Integral dt by 1 plus t squared. You're confused a little bit. Where?
d of x by a.
No, I wrote dx as d of a into x by a. Tell me, is it okay so far? And then, can this a not come out of the differential sign because it's a constant? So it comes out of the differential sign, right? Now when it came out of the differential sign, it stood there and then it was ready to take care of 1a in the denominator, brought it down to 1 by a, right? Then d of x by a by 1 plus x by a whole square. So in any case, we have this integral reduced to a known form, 1 by a integral dt by 1 plus t squared, and that's going to be integral tan inverse t, where t here is x by a, right? Plus c, 1 by a tan inverse x by a plus c. So yet another standard integral, integral 1 by x square plus a square is 1 by a tan inverse x by a plus C. Got me? I will. See, this was a known integral, 1 by 1 plus t squared dt, that's tan inverse t plus c, alright? Now we have a variant to this form, which is 1 by x squared plus a squared. Now, all the algebra that I carried out there was my attempt to bring it to this form, right? So, at the very onset, I took a squared common from this, leading to 1 plus x by a whole square. Yes or no? Right? And then this dx was written as d of a into x by a into x by a. When this a was a constant, property of differentials, this came out of the d sign. This became 1 by a then. And then we have integral dt by 1 plus t squared, isn't it? dt by 1 plus t squared, where t is x by a. Integral dt by 1 plus t squared, that's tan inverse t plus c. So that's like tan inverse t. T is x by a plus c.
So one thing, sir, integral 1 by 1 plus t square dt. So that is tan inverse t plus c. So if 1 by a is outside, so it is 1 by a into the...
No, this 1 by a anyway sticks out. Forget this 1 by a. It's 1 by a into this.
Why not into c? Why not c by a?
But c by a is also a constant. C is an arbitrary constant. Agreed. So c by a will also be an arbitrary constant. Okay, if I had said this plus c, this c I can call as an arbitrary constant, right? And this 1 by a clubs with this arbitrary constant by a would still be an arbitrary constant, and that arbitrary constant can still be referred to as c, right? C divided arbitrary constant divided by a will still be an arbitrary constant, and that new arbitrary constant could be referred to as c. There's no loss of generality in doing this. Are you all okay with everything that I've said here? Now, one by x squared minus a squared dx. Integral of this form. 1 by x squared minus a squared dx. This x squared minus a squared can I not write as x minus a into x plus a? Right? I could do this, right? And then the numerator could be written as x plus a minus x minus a. But that makes it 2a. There was a 1 here. What I do is I divide by 2a. Could I do this? You know what I did here? I wrote 1 as x plus a minus x minus a. That made it 2a. But then I divided by 2a so that it's restored to 1 again. Right? So this algebra is clear to you? Right? And then when I divide this divided by this minus this divided by this, but this divided by this is 1 by x minus a. Minus this divided by this is 1 by x plus a. Right? So far so good? Veda. This 1 is written as x plus a minus x minus a, which is 2a divided by 2a. This is 2a divided by 2a, that's 1. Right? And this x squared minus a squared I wrote as x minus a into x plus a. And then this difference is like x plus a divided by this minus x minus a divided by this. But x plus a divided by this is 1 by x minus a, and x minus a divided by this is 1 by x plus a. Right? So 1 by x square minus a square could be written as 1 by 2a to 1 by x minus a minus 1 by x plus a. Got me? So what I do here is I write this x square minus a square as 1 by 2a into 1 by x minus a minus 1 by x plus a dx. Then integral of the difference would be difference of the integrals, like I told you in my last class. Right? This is integral of the difference of two functions. That would be difference of the two integrals. So that's 1 by 2a integral 1 by x minus a dx minus integral 1 by x plus a dx. Clear? 1 by 2a is outside. Integral fx minus phi x. Integral f1x minus f2x would be integral f1x minus integral f2x. Right? I suggested this in the last class, didn't I? Towards the end of my last class, I gave you this. What according to you should be this? 1 by x minus a dx. What's the derivative of x minus a? Derivative of x minus a. ddx of x minus a is what? 1, isn't it? ddx of x minus a is ddx of x, which is 1, minus 0, which is 1. ddx of x minus a is 1. Numerator, the derivative of the denominator, yes or no? Numerator, the derivative of the denominator. So this integral would be log mod denominator, log mod x minus a, yes or no? Come to this. What's the derivative of x plus a? 1. The numerator is the derivative of the denominator. So the integral would be log mod x plus a, log mod x plus a precisely. So this is 1 by 2a log mod x minus a minus log mod x plus a, and then a constant of integration consolidated. Constant of integration consolidated. Out of both these integrals, a constant would emerge. I've clubbed both the constants together and represented as one single constant c. So far so good? And then log a minus log b is what? Log a by b. Log a minus log b is log a by b. And that causes this to become 1 by 2a log mod x minus a by x plus a plus c. Right? So 1 by x square minus a square is 1 by 2a log mod x minus a by x plus a plus c. This is yet another standard integral. You got to remember this. 1 by x square minus a square is 1 by 2a log mod x minus a by x plus a. Comfortable? All of you? Integral 1 by root a squared minus x squared dx. This, of course, is slight departure from the following integral. 1 by root 1 minus t squared dt. What was that supposed to be? Sin inverse t. That was sin inverse t plus c. Now the departure is that you have a square instead of 1. So the first level of thinking would be to make this 1 somehow, right? How are you going to make this 1? By taking a squared common from this expression, take a squared common. The moment this a squared has to transcend this square root sign, come out of the square root sign, it's going to become an a, right? So I take a squared common from this expression, allow it to break past the square root wall. When it comes out, it becomes a, right? So then 1 by a. Reason we did this manipulation is that somehow I wanted a 1 here so that by hook or by crook I could reduce it to this format, right? So then 1 by root 1 minus x by a whole squared. So far so good, right? But now if I have a t here, I have a t there, right? So if I have a x by a here, I would rather want a x by a there, so that there is complete mapping from this form to this form. Yes or no? Right? So then, like before, I want x by a to become my new subject. X by a. But then this a would have to be manipulated here. And then this a finds a thoroughfare outside. This a goes out like before. Right? And when it moves out, it takes care of this a, dissolves this a. Right? And then you have like integral dt by root 1 minus t squared, integral dt by root 1 minus t squared, and which is supposed to be sin inverse t, where t is x by a. T is x by a. Sin inverse x by a plus c. This one. From this, I took a squared common, right? So when I took a squared common, I was left with 1 minus x squared by a squared. But square root of a squared, that was a when it came out. So it comes out and it becomes like a 1 by a, which is what we had here, right? And then this I wrote as x by a into a dx. Reason, because I wanted the same thing to be mapped there, x by a. So I wrote it as a into x by a, and then this a migrated out. And this migrated out, it took care of this a. So integral dt by root 1 minus t squared, integral dt by root 1 minus t squared, that's sin inverse t plus, right? Which is what I'm trying to do. So integral root 1 a squared minus x squared is going to be sin inverse x by a plus c. Are you all there with me on this? All right. So by this time, we've looked at variations in differentiation. We've looked at some basic integration, some standard results in integration. Differentiation was by and large governed by a sum rule, a difference rule, a product rule, a quotient rule, and eventually a converging chain rule, right? It's summed up in any function on the face of this planet could be differentiated by a combination of these rules. Integration, though, had a different philosophy to embrace. It was more about a set of standard integrals, and the objective was, if you encounter any other integral, a set of integrals was presented to you. And then any other integral that you encountered had to be reduced to one or more of these integrals and then taken care of, right? It was not too much of rule intensive. It was about converting a certain expression into a known format and then relating to that format, write down the answer. That's what you did in an integration. So integration was about benchmarking, was about referencing, not too much about rules. Differentiation that way was little more liberal and open. It was about applying those rules, sum rule, difference, product, quotient rule, chain rule effectively, right? Now, so like I said, any function you would have to reduce to a known function. In integration, any function you would have to reduce to one of those standard integrals and then deal with it. For example, did I tell you how to integrate cos squared x? If all of a sudden you encounter a cos squared x, which for sure does not lie in your kitty yet, right? It's not there in your kitty yet, right? What you might want to do is you will have to then rely on your trigonometry acumen. Cos square x, if you recall, is half of 1 plus cos 2x. Cos square x is half of 1 plus cos 2x, right? You remember those results in trigo? Cos square x is half of 1 plus cos 2x. Right? No? You're not familiar with this result? Confused? Confused about this result a little bit? Yeah, no. So cos squared x is half of 1 plus cos 2x. Then integral of the sum of two functions would be sum of the integrals. So this is like half of integral 1 into dx plus integral cos 2x dx. How about this? 1 is like a x bar 0. So this would become x bar 0 plus 1 divided by 0 plus 1. So I'm going to combine the constants eventually, write it as one single constant. So I'm not going to give one constant for this and one constant for this. At the very end, I'll just put one consolidated constant, right? So then this is like a half of x plus, now cos mx dx. Integral cos mx dx is sin mx by m. Is not minus sign, is sin mx by m, right? So sin 2x by 2, and there is a constant that has emerged from this, a constant that has emerged from this, and then there is a half multiplied by the combination of that constant leading to yet another constant, right or no? So that's plus c, a consolidated constant that came out of each of these integrals. This is plus c. Yes. Integral 1 dx is integral like x bar 0 dx, right? And integral x bar n dx is x bar n plus 1 by plus c. So x bar n dx is x bar n plus 1 by n plus 1. So which is x. Now if I asked you to integrate sin squared x dx, did you all understand this? So what did we eventually end up doing? We had to convert this cos squared x into known integrals. One was a known integral, cos mx was a known integral. That's what we had to eventually do, right? So integration, like I said, is about referencing. You have database of integrals and you would have to reduce each integral to one or the other format. Clear? This one. So integrate sin squared x dx now. Got it? Got it? Sine squared x, like I said, is half of, right, is half of 1 minus cos 2x. Half of integral 1 into dx minus integral cos 2x dx. This is x power 0. So this would give me x. Cos mx would give me sin mx by m. And then there is a right. Then why don't you try your hands on cos 3x cos x, integrate cos 3x into cos x. Cos 3x into cos x. Cos A cos B. Cos A cos B. Cos A cos B. Huh. Once bitten, twice shy.
Cos A cos B equals to half cos A plus B. So I'll say half cos A plus B plus cos A minus B.
Oh, okay. Thank you. You almost were geared to provide another round bout of entertainment to us. Oh God, we just missed it. Okay, so cos A cos B, half cos A plus B plus cos A minus B. Half cos A plus B plus cos A minus B, right? Reduce it to a known format, right? Which is, yes or no, half cos A plus B plus cos A minus B. So which is like half of integral cos 4x dx plus 2x dx, right? Integral, see this I wrote cos A cos B is half cos A plus B plus cos A minus B. Integral of the sum is sum of the integrals, right? Which is half of, now cos mx is sin mx by m. Cos mx sin mx by, and then there is plus. So again, see, this was not given to you, but you had to reduce it to known forms. These were known forms. Integral cos mx was known to you, right? Are you all there with me? Did you all understand this? Okay. Yes.
We would write the formula for cos 3x and use the product to differentiate.
What is the? But we are integrating. We are not differentiating. If that rule existed in integration, the same product rule that existed in differentiation, I'll tell you, it would be simply wondrous. We got me? And then, of course, sine 5x, sine 2x, sine A, sine B.
Sine A sine B is sine A cos B. Oh no. So that is sine A plus B. Sine A sine B is half sine A minus B minus half cos A minus B minus cos A plus B.
Be sure about what you're saying. You've given me 5 options. I'm not supposed to pick one from there. This is your last opportunity to get it right.
Half cos A minus B minus cos A plus B.
I know for many in the class it was disappointing when you answered it right, because there would be 10 hours of respite from integration and some nursery rhymes, etc. So this is like half of cos A minus B minus cos A plus B. Cos A minus B minus cos A plus B, right? Which is half integral cos 3x dx minus integral cos 7x dx, right? Integral of the difference is difference of the integrals. Sin A sin B is half cos A minus B minus cos A plus B, right? But cos mx is sin mx by m plus c. Okay, then I figured out you know that. Now I'll have to catch someone else. Okay, you want to answer?
Yes.
Okay, answer.
So half sin A plus B plus sin A minus B.
Oh, okay. Good. So sin A cos B, half sin A plus B plus sin A minus B. Right? Sin A cos B, half sin A plus B plus sin A minus B. Then integral of the sum would be sum of the integrals. So half of integral sin 6x dx plus integral sin 2x dx. Hey, what's integral sin mx? Minus cos mx by m, right? So sin 6x would be minus cos 6x by 6. So that's going to be half of minus cos 6x by 6, and this would be minus cos 2x by 2. And then there is a neat c sitting there. What about integral sin cube x dx? Integral sin cube x dx. Please integrate sin cube x with respect to x. No. That's t to power t cube dt is t to power 4 by 4. But is it like t cube dt? No. If it was sin cube x d sin x, then it would have been sin to power 4x by 4. Integral t cube dt would be t to power 4 by 4. But now sin cube x dx. And then do what? There is no product rule that you're aware of. And then do what? Okay. No, you sine cube x is indeed sine squared x into sine x, and then do what? Huh? Yeah, but then do what? Sine squared x into sine x, and then what? Yeah, but then you'll have cos squared x sine x again. Why would you not think sine 3x 3 sine x minus 4 sine cubed x? So sine cubed x is 1/4 of 3 sine x minus sine 3x, 1/4 of sine x minus sine 3x, yes or no? Hey, sine 3x is 3 sine x minus 4 sine cubed x. So sine cubed x would be 3 sine x minus sine 3x by 4, right? So might as well write this sine cubed x as 1/4 . Tell me. That's a formula that was discussed in trig. You survived. You like very close, huh? So then this would be 1/4 of integral 3 sine x dx minus integral sine 3x dx, right? And then this 3 can come out of the integral sign. But what's integral sine x? Minus cos x. Integral sine x is minus cos x. Integral sine 3x is minus cos 3x by 3. Integral sine mx is minus cos mx by m. Right? So then this is 1/4, 3 times minus cos x minus sine 3x is minus cos 3x by 3. Plus a consolidated c. Got it? Oh, sorry. You want me to write it again? Some basic stuff done, right? An integration. I'll give you a 10-minute break. Relax for 10 minutes, chill out. If you like, just take a deep breath in the balcony there or move out on the road. Shout your heart out. Alright? One of the things that they do in Japan is, in industry, in corporate houses, I'm not sure if I want to do the same thing, but they have certain rules in which they have bosses made out of cotton and clay, and the employees can go and hit the bosses and vent out their emotions during a break. I don't know how close I can come to that, providing you the infrastructure to be able to do that during a break time. But if it was not an educational setup, maybe I would have given you that. And if it was not India, perhaps it was an educational setup in the US, I wouldn't care. I would give you a Malai Khandelwal made out of cotton, bang and boom, bam, boom, bam during a break, and then feel settled, come back, ready to receive more. But the least that I can offer to you is go out and say things that you want to and then come back. Once you are relieved, come back. And now, the reason we've been doing all this, let's say there is a particle moving along a straight line. Call that straight line as the x-axis. Why not? Right? And let's say the x-coordinate of the particle as a function of time. The x-coordinate of the particle as a function of time is given by t cube plus t squared. The particle moves along the x-axis and its x-coordinate given by t cube plus t squared. Now, I want to find the velocity of the particle as a function of time. Velocity is, after all, rate at which x changes with time. Velocity is rate at which x changes with time. That means the velocity is given by ddt of x. Velocity is rate of change of x coordinate with time. That's the velocity, right? That's the definition of the velocity for a particle moving along a straight line. Which is like, differentiate x with respect to time is like a 3t squared plus 2t. So velocity at any given instant of time is given by 3t squared plus 2t, right? That means at t equal to 1, for example, the velocity would be 3 into 1 squared plus 2 into 1. At t equal to 0.7, the velocity is going to be 3 into 0.7 squared plus 2 into 0.7. The acceleration of the particle is rate at which velocity changes with time. Acceleration is rate at which velocity changes with time. That means ddt of v. And rate at which velocity changes with time is like a 6t plus 2. That means at any given instant of time t, you can find the acceleration of the particle, right? Now, so if somebody tells you how a particle is moving along a straight line, let's say gives you the rule by means of which it travels along a straight line, then you can differentiate that to obtain the velocity of the particle. You can obtain the acceleration of the particle. But suppose somebody prescribes the following. He says the acceleration of the particle at any given instant of time t, the acceleration at any given instant of time t is t squared plus 1, is t squared plus 1 meters per second squared at any given instant of time. And you are asked to find the velocity of the particle as a function of time. You are asked to find the velocity of the particle as a function of time. And what you do is write the acceleration as dv dt, rate of change of velocity with time. That's acceleration, right? And then what you might want to do is you could treat this as a ratio dv by dt, and therefore the luxury to multiply with the dt throughout. So then this would give you like a dv equal to t squared plus 1 dt. How about this? Right? Now integrate both sides. Integrate both sides. But what's integral dv? What's integral dx? X. So integral dv would be v plus a constant of integration, right? Now I'm going to combine both these constants into one constant, right? So I'm not going to write separate constants for this integral and this integral. I'll just club them together. Okay. What is integral t squared dt? T cube by 3. Integral x power n dx is x power n plus 1 by n plus 1. So integral t squared dt would be t cube by 3. Integral 1 dt is t. See, this is integral t squared dt plus integral 1 dt. Yes or no? Integral t squared dt is t cube by 3. Integral 1 dt would be t, right? And then the two constants, all the constants that emerge, club together as one single consolidated constant, right? Now the thing is, you don't have complete knowledge about the velocity of the particle, right? Because this c, if somebody says what was the velocity at t equal to 4 seconds, then you're ill-equipped to answer that question, because the c comes as an obstacle. You do not know the value of c, right? Which means if somebody has just prescribed the acceleration as a function of time, then that data is not enough. Why? Because we still have c to comply with. We don't have the value of c available to us. Therefore, there is need to furnish more information. What kind of an information? Let's say, after all, data has been provided by an observer. Data has been provided by an observer. There is an observer that reports at as t squared plus 1. The observer now tells you that at a certain instant of time, let's say at t equal to 1 second, he says at t equal to 1 second, he found by some means, alright, he found by some means that the velocity of the particle at t equal to 1 second was 1 meter per second. This is one data that he reports to you. He doesn't have complete information about the velocity at every instant of time, but he has knowledge of the velocity at some instant of time. At some instant of time. He says, for example, at t equal to 1 second, he observed or he found through his spies that the velocity was 1 meter per second. Now, this gives us an opportunity to compute the value of c, because when t is 1, v is 1. When t is 1, v is 1. So put t equal to 1, put t equal to 1 and v equal to 1 in this equation. You get 1 equal to 1/3 plus 1 plus c, right? That makes c equal to minus 1/3. C equal to minus 1/3, right? So now that you have knowledge of this c, you can plug into this equation c equal to minus 1/3, and now the complete velocity profile of the particle is available to you. You have velocity at each and every instant. All that you need to do is plug in the value of t, any instant of time, you get the velocity at that instant of time, right? So from acceleration, one level of integration led to velocity, but it was not enough because there was a constant to deal with. To deal with the constant, one set of data was required. This, for example, was one data which enabled computation of c, and a data of this kind, an information of this kind, a condition of this kind is often referred to as a boundary condition. A boundary condition. This is referred to as a boundary condition. A boundary condition. The boundary condition would be required to compute constants of integration at various places as and when required. Alright. So one boundary condition along with one level of integration from acceleration to velocity, the journey involved an integration and then eventually computing the value of the constant of integration with the help of a boundary condition. Alright. I mean, the condition could have been something else also. It could have been, well, he might have observed at t equal to 0, the velocity was 4 meters per second. And then commensurate with that condition, the computation of c would take place. Alright, so for different situations, you will have different c's. Now, and it's not like from now on, you're not going to assume that motion started at t equal to 0. This t is synthetic, man-made. Alright. the motion could have prevailed prior to t equal to 0. If I choose to call this instant as t equal to 0, then when the class started, it was t equal to minus 2 hours, for example, right? Okay. At 7:30 or 8:30, the class, that instant of time would be t equal to plus 2 hours. T equal to 0 does not mean that there was no activity prior to t equal to 0. It's just that I choose to call this instant as t equal to 0. Instance prior to this must have been negative instance of time. Instance after this must have been positive instance of time, right? So t equal to 0 does not mean that there was nothing physical about instance of time less than 0. No. All activity could have prevailed prior to t equal to 0 as well. Alright. So negative instance of time are not garbage. Okay. They could very well have physical meaning. Okay. Now I have velocity as a function of time. At any given instant of time, I can compute the velocity of the particle. And now I want to know the x coordinate of the particle as a function of time. So what I do is, I write this velocity I know is rate of change of x with time. If the particle is moving along the x direction, then rate of change of x with time is the velocity, right? So call this as dx dt, call this as dx dt, right? So then we have dx dt as t cubed by 3 plus t minus 1/3, right? Or dx then is t cubed by 3 plus t minus 1/3 dt, right? Integrate this. Integral dx would be x. Integral t cube would be t to the power 4 by 4. Differentiate नहीं करना, integrate. Integral t cube would be t to the power 4 by 4, right? Integral t to the power n dt is t to the power n plus 1 by n plus 1, right? T to the power 4 by 4. So this is t to the power 4 by 12. 4 into 3, 12, right? Minus plus integral t dt would be t square by 2. Hey, are you lost? You understanding this, no? Integral t dt would be t square by 2 minus 1/3. Integral dt would be t. Integral 1 dt would be t. So t, and then there is a constant c prime that emerges. So now again, you are not ready to compute x at any instant of time. Why? Because c prime is still unavailable, right? So c prime would have to be computed based on yet another boundary condition, right? There is need to have yet another boundary condition so that c prime could be computed, right? Somebody might tell you that at time t, for example, at time t equal to 0, the particle was at the origin. At time t equal to 0, the particle was at the origin. That means x was 0. This could be given, for example, this could be a boundary condition, right? At t equal to 0, x was 0. All right. So when at t equal to 0, x was 0, put x as 0, t as 0, what happens to c prime? C prime turns out to be 0, right? C prime turns out to be 0, right? So with this condition, c prime turns out to be 0, and then you know x as a function of time, the x coordinate of the particle as a function of time, t to the power 4 by 12, this plus 0, right? So you could start with x, differentiate to get the velocity, differentiate a second time to get the acceleration, or so if you go from x to v to a, there you don't need any boundary condition, right? Because you carry out a differentiation which does not involve emergence of a constant, right? But when you start from a and move on to velocity, it involves an integration, a constant of integration emerges, and then when you go from velocity to x, you integrate again, and yet another constant emerges. So you would call for yet another boundary condition, right? So then this will constitute the backbone, this kind of an operation would constitute the backbone of all the kinematics that we are going to learn down the line. All right. What I want to do is, I just want you to get hands-on with things of this sort. Okay. There's a particle moving along the x-axis, there's a particle moving along the x direction, and its acceleration as a function of time is sine t plus e power t. It's sine t plus e power t. Find velocity as a function of time to displacement x or the x coordinate as a function of time, given that at t equal to 0, the velocity of the particle at t equal to 0 was 0. Let's say the velocity at t equal to 0 was 0 meters per second. All right. Also, it's given that at t equal to 0, or it could be, let's say, pi by 2. At t equal to pi by 2, the velocity of the particle at pi by, or rather the x coordinate of the particle at pi by 2 was 1. Find velocity as a function of time to x as a function of time. Take a few more. I give you velocity as a function of time as sine t whole squared into cos t. Sine t whole squared into cos t. Find 1 x as a function of time, 2 acceleration as a function of time. Given that at time t equal to 0, x was 0. Given that at time t equal to 0, x was 0. All these particles moving along the x direction. 3. Acceleration of the particle at t given by t cube plus t into the power half into 3t squared plus 1. Find v as a function of time, given that at time t equal to 0, v was 0. V at time t equal to 0 was 0. Find v as a function of time. Please do all this. First problem, where acceleration is, I need some working space here. Acceleration is dv dt, which is sine t plus e power t, right? dv therefore is sine t plus e power t dt, right? Carry out an integration. Integral dv would be v. Integral sine t would be minus cos t. E power t would be plus c. How does one arrive at c? From the fact that at t equal to 0, v was 0. It's given in the problem. That's one boundary condition, right? At t equal to 0, v is 0. So put t equal to 0 and v as 0. 0. Cos 0, 1. So minus 1. E power 0, 1 plus c. So c is 0. C is 0. So all of you got this right? Right? So c is 0. So I get velocity as a function of time. V is minus cos t plus e power t, right? And then, but velocity is rate of change of x with time. If a particle is moving in the x direction, velocity is rate of change of x with time. So then I get like a dx equal to minus cos t plus e power t dt. How about this? Integrate both sides like before. Integral dx is going to be, now cos t would be sin t, cos t would be sin t, therefore minus with, minus sin t, and e power t would be plus a c prime. And how does one comply with c prime? Another boundary condition, at t equal to pi by 2 x was 1. At t equal to pi by 2 x was 1. So put t equal to pi by 2, this becomes 1. So x is 1 minus 1 e power pi by 2 plus c prime. So then c prime is 2 minus e power pi by 2. All of you got this right? So this c prime you can plug in as 2 minus e power pi by 2 and you would get x as a function of time. You're going to get x as a function of time. Right? So that was the first problem. I hope all of you got it right independently as well. Right? And I hope all of you have understood everything that we did here. Good. Now for the second problem, Vt is sin t whole square into cos t, right? X as a function of time. So V I can write as dx dt. V I can write as dx dt. Dx then could be written as sin t whole square into cos t dt. Carry out the last right. Integral dx is going to be x. Now, what's this? Function raised to a certain power into the derivative of the function. Realize that? This is sin t raised to the power 2 and this is the derivative of that function. Function to power n plus 1 divided by n plus 1. How about that, right? This is sin t function raised to the power 2 into the derivative of sin t, which is cos t. Function raised to a certain power into the derivative of that function. So that's going to be function to power n plus 1 divided by n plus 1. How about that? Right? So this is sin cube t divided by 3 plus c. And then, I gave you boundary conditions. I wiped them off, so I don't remember what boundary conditions. When x is 0, t equal to 0. That's what I prescribed. So that will give me c equal to 0. So in the boundary conditions, I said when x is 0, t is 0 when x is 0. T is 0 when x is 0. So then put t equal to 0, x is 0. That will bring c to be 0, right? So that will make c equal to 0. So then I get x equal to sin cube t, x equal to sin cube t. How about that? Right? So I know x as a function of time. Is that okay? Are you confused? No? You're not consuming human flesh, right? No liquor? Now, how about acceleration? I want to differentiate v as a v with t, right? dv dt would give me acceleration, right? That is d dt of sin squared t cos t, right? Product rule, right? Derivative of first function into second function plus derivative of second function into first function, right? So this is like d dt of sin t whole squared into cos t plus sin squared t into d dt of cos t. How about this? What's d dt of sin t whole squared? Chain rule, go from outside to inside. Absolutely, 2 sin t into cos t, right? 2 into sine t to the power 2 minus 1 into cos t, right? ddt of sine t whole square. Something to power m into something to power m minus 1, 2 into sine t to power 2 minus 1, and then come to sine t inside, that's cos t. So that makes it 2 sine t cos t. 2 sine t cos t, right? All of you have understood this? ddt of sine square t is 2 sine t cos t, right? Alright, so this is like cos t into 2 sine t cos t plus sine square t, and ddt of cos t is good. So we have acceleration as a function of time. Yes or no? We have acceleration as a function of comfortable? Absolutely. Can I wrap this up? How many of you got this right independently? Okay, where were you stuck up? Integration of sine square t cos t, right?
Yes.
It didn't occur to you that its function raised to a certain power into the derivative of the function. Okay. Different way, मतलब sin square t को लिखा 1 minus cos square t, cos cube t को integrate किया using cos 3t का function. Yeah. It's like, okay, I'll tell you later.
Sir, I took sin square t outside and then sin t cos t I took it as sin 2t by 2. And after that,
You wrote this as sin t into half sin 2t. And then sin A sin B. Half cos A minus B. Okay, very good. What's your name? Very good, Shubham. Yeah, so I really like what he did. You know? Good. I mean, what he did was the following. He wrote this as sin t into sin t cos t. Right? Which is like sin t into, this is half sin 2t. This is, right? Sin A cos A is half sin 2a. So that's half sin 2t. And then our friend said it's like sin A sin B, half cos A minus B minus cos A plus B. So 1/4 sin A minus B minus or cos A minus B minus cos A plus B. Sin A sin B is half cos A minus B minus cos A plus B. Right? And then these were ready to integrate. This, and when you integrate this, it will be sin t. This will be sin 3t by 3. So good job done. Very good. No, you didn't understand. Nothing, no? I'll explain again. Okay, did you understand what I did? Okay, but it makes sense to understand this also. This sin square t is sin t into sin t cos t. Alright?
So now I understand.
The rest have understood everything? Huh? What was the third problem? I wiped that out. Can you tell me? What's your name? Not going to use your mobile. When you come to the class, the most preferred scenario is to switch it off. That's one. You're sitting right in front of me and you're tinkering with your mobile. No. That you did once you found me. Observe this. Don't play with your mobiles. It's a message to all of you. I can be really crooked and violent and wild and unscrupulous. Guard yourself against all the vehement attacks that could come out of me. I'm absolutely dangerous. My mild manners occasionally are nowhere close to reflection of my profile. Okay, I'm extremely notorious. My background is that I hail from Birla High School till class 10, and you realize that I imbibed, in addition to a lot of education that I received there, um, I imbibed a lot of hooliganism out of that place too, and obviously over a period of time I clipped myself, trimmed myself, matured, uh, made myself look bourgeoisie and savvy, uh, and good and graceful, but all those things were still passively present in me. When the time arises, the Birla high in me becomes prominent. All right, which means any departure from prescribed rules in the class will cause the Birla high in me to start breathing. All right. Credit to all the Birla high education that I received. That's only one side of the story, but then there is the other side of the story too. All right. So the smile is very fictitious. All right. Don't believe in the smile. Okay. What was the third problem in any case? All right. Acceleration is dvdt. Acceleration is dvdt. Three t squared plus one. Right. dv then is like a t cube plus t to the power half into 3t squared plus 1 dt. What do we do? Integrate. Integral dv would be, this is function raised to a certain power into the derivative of the function. Realize that the derivative of this is 3t squared plus 1. 3t squared plus 1. Right? So that makes it like a t cube plus t power half plus 1, 3 by 2 divided by 3 by 2 plus. Now it's given in the problem that at t equal to 0, v was 0. Right? So when t is 0, if you put v as 0, you arrive at c equal to 0, right? If you put t equal to 0 and v equal to 0, c turns out to be 0. So when t is 0, v is 0, that's the boundary condition. C turns out to be 0. So then if c turns out to be 0, this becomes velocity as a function of time. Velocity as a function of. Got it? Well, the reason I just took a little detour from maths and brought you to terms with some of this motion related stuff, just to drive you to the point that eventually this is the reason we learned all the calculus that we've done so far. When I meet you on Wednesday, what I want to do is